Okay, thank you very much. I'll be speaking about new hope for post-quantum key exchange. And this is joint work with Erdem Alkem, who's at Ege University in Izmir in Turkey, Leo Ducat, who's at CWI in Amsterdam in the Netherlands, Thomas Pöppelmann, who's at Infineon in Munich in Germany, and myself, and I'm also in the Netherlands in the University of Nijmegen. Let me start my talk by a quote. And it's a quote from about 4 years ago by Mark Katchen, who's doing research at IBM. And he's doing research on quantum computers and on, well, eventually building a large universal quantum computer. And in 2012, Mark Katchen said that in the past, people have said, maybe it's 50 years away, it's a dream. Maybe it'll happen sometime. I used to think it was 50. Now I'm thinking like it's 15 or a little more. It's within reach, it's within our lifetime, it's going to happen. So why would we care as cryptographers if somebody builds a large quantum computer? Well, essentially it means that if researchers do that, if quantum engineers, if physicists are able to build such a computer large enough, maybe in the next 2 decades, then that's the end of crypto as we know it. Or maybe a bit more specifically, it's the end of asymmetric crypto as we know it. And the reason for this is that in 1994 already, Ashore published an algorithm which already in the title of the paper, says it's doing 2 things, 2 very special things, namely it's factoring integers in polynomial time on such a universal quantum computer, and it's computing discrete logarithms in polynomial time on a big universal quantum computer. Now these are essentially the 2 problems that all of our current asymmetric crypto is based on. So for example, this would mean a complete break of RSA, of Al-Gamal, of DSA, Diffie-Hellman key exchange, all the elliptic curve variants thereof, so ECDSA, ECDH, at DSA, whatever you want to come up with. So that's pretty scary, but well, it feels like it's still like 1 or 2 decades away, right? So, you know, let's maybe do some research, let's get some cool stuff done, and maybe we can find solutions to this. But actually, the situation is even worse. Imagine an attacker has been named in the question and answers of the previous talk, for example, an attacker using large data centers to record internet traffic, encrypted internet traffic today. And then maybe in like 1 or 2 decades, when this attacker has a large quantum computer, it's just going back and decrypting all that traffic that has been recorded before. Now, honestly, for some of the communication that I have on the internet, which I encrypt, in 20 years, I probably don't care anymore. But for some communication, some people really do care, and that would probably be exactly the communication that this attacker would target. Now, sometimes when you're looking at this kind of attack where somebody's recording today and then later looking back at it, people say, wait, we have perfect forward secrecy. That's a great concept, but it doesn't help. So the idea in perfect forward secrecy is to use long-term keys only for authentication and use short-term ephemeral keys for encryption. And the idea is that if the long-term keys get compromised, for example, by somebody breaking into my laptop and stealing all my keys, it's not possible to just go back and use those keys to decrypt all old information, because it has been encrypted under short-time ephemeral keys that have been immediately deleted. However, that doesn't help against a cryptographic break, because you can just go back to all the recorded traffic and break one of the key exchanges after the other. That's a linear slowdown, but that's still not particularly good if you have a polynomial time algorithm to break stuff. Now, I'm not saying that perfect forward secrecy is bad. We definitely want this. It's giving us a very, very strong protection against a real-life, real-world issue. So what we want today is post-quantum, perfect forward secret crypto. And obviously, if we want this, we can't build it on the problems that I wrote down above. So we can't build this on discrete logarithms, as in Diffie-Hellman, for example, or elliptic curve discrete logarithms, or on factoring. So there needs to be some other problem which we can use to build asymmetric crypto, and more specifically that we can use to build ephemeral key exchanges that quantum computers, as far as we know, do not completely break. Here's that problem. Well, at least the problem that I will use for the rest of the talk. There are some others. So the problem that I will use in the rest of the talk is called the ring learning with errors problem. And I will use this slide to introduce a bit of notation. So what we will need is one mathematical structure that we're working in, and that is this ring RQ. And the ring RQ, that's simply polynomials in a variable x. And all the coefficients are taken modulo an integer q. And then, so that the polynomials don't grow arbitrarily in multiplications, we reduce them modulo some polynomial, and that polynomial is x to the n plus 1. Okay, so then we need chi to be an error distribution on this ring. So typically something that chooses with small errors. We will come back to that in a bit. And then we have a secret. We always have some secret in asymmetric cryptography. Well, in almost all of cryptography, that's S, and that's just an element of this ring. And now the attacker is given pairs of A and AS plus E, where A is uniformly sampled uniformly at random from this ring RQ, and E is sampled from this noise or error distribution chi. And the task for the attacker is to find S. So that's the problem that we're going to base the crypto on that I will be talking about. There's two very common choices here. One very common choice for chi is to use the so-called discrete Gaussian distribution. It's very nice, gives very nice mathematic properties. It allows to prove certain properties here. It's not so nice when you have to implement this. So typically when you implement a high-quality discrete Gaussian, you end up with either very inefficient implementations or implementations that leak through timing information about the values of this noise distribution, which is something that we really want to avoid in the real world. I will come back to this later because we decided not to use a discrete Gaussian. Then there's a very common optimization, and that is to use the same A for all users. So you don't need to resample this every time. You just do this once and you compile it into your software. We also didn't do that, and I will also come back to that later. Let me give you a bit of a history of how this ring LWE and some variants of it have been used. This is completely not a complete overview of the history. You can find like typically tens of papers every year being published in this area. But it's sort of a bit of the history that builds up to, well, what I'm presenting in this talk. In 1996, Hofstein, Pfeiffer, and Silverman presented the N-true crypto system, which is still around today. It can be seen maybe as a bit of a predecessor to ring LWE. It can maybe also be seen as a bit of a competition. So it's similar but a bit different. But that was sort of the first crypto system that is, well, that survived and that is still, that appeared in this realm related to ring LWE. Then in 2005, Regev introduced LWE-based encryption. So that's learning with errors without the ring. And essentially then polynomials turn into large matrices and vectors. So that means that keys typically become quite a bit larger, and you can think of the ring LWE version as a specialized version of LWE, where these large matrices have a certain structure that allows us to compress, compress the matrix. In 2010, Lyuboshevsky, Picard, and Regev introduced ring LWE, and then also, while based on ring LWE-based encryption. And 2 years later, Dingxie and Lin showed how to transform this into a key exchange protocol. This was improved by Picard in 2014. In particular, Picard showed how to obtain keys that are not biased. And interestingly, in this 2014 paper, there were no parameters that you could just take and implement this thing. So I'm looking at this from a person who's writing some cryptographic software from time to time. That paper was not actually telling you what to really implement. There was a follow-up in 2015 by Boss, Castello, Neric, and Stabila. What they did is they chose parameters for this key exchange proposed by Picard in 2014, and they implemented this, and they integrated it into OpenSSL, and showed that you can actually, in TLS, do post-quantum key exchanges using this approach. Now, the parameters that they chose were, well, this ring RQ, as I showed it before, polynomials of n coefficients, with each coefficient being an integer mod q, where n is 1024. As q, they chose 2 to the 32 minus 1. For those of you who are interested, that's not a prime. It's obviously a 32-bit integer. And as a noise distribution, they chose exactly what I mentioned before, this discrete Gaussian with standard deviation sigma of something like 3.192. And what their paper claimed was that they have 128 bits of security, but only pre-quantum. So they did not look at, okay, so what happens if an attacker has a big quantum computer? As far as we know, the attacker doesn't break this in polynomial time. Otherwise, well, we would be in very serious trouble. But that doesn't mean that a large quantum computer can't do anything. They didn't analyze that. They just said, well, pre-quantum, currently 128 bits. And then they had a failure probability in there, which was extremely small. So something like 2 to the minus 131,000. This idea of a failure probability is essentially that if you make the noise too large, then at some point everything will fail. If you make the noise too small, it will become insecure. Very obviously, if you set the noise to 0, you can solve the whole thing just with Gaussian elimination. And if you make it too large, then it doesn't help. So basically, this noise balances between security and failure probability. And the failure probability was enormously small. OK, so what we decided is let's reconsider this, and let's see whether we can do better in terms of security, in terms of performance, and let's see where we get, and whether we can make this maybe a bit more practical, because the performance, well, we will see numbers later, was not as good as it can be. Before I look at what we did, let's look at the protocol, because this is a pretty nice, well, sort of easy version of how this key exchange works. So again, up here you have the system parameters, as I mentioned them before, with the other distribution, and then there's some global system parameter. That's this A. And as I mentioned before, they use this optimization of saying, here's a global A. Then Alice, the server, samples some S and E, and actually S is also sampled from this noise distribution. That's a common way to do it. And then computes B, which is AS plus E. So that's exactly this computation that we saw before, which is then handed over to an attacker. And yeah, it is handed over to an attacker, it's sent over the channel. And then Bob receives this and does two very similar computations here to compute U and V, and then sends U over to Alice. And Alice multiplies that by S and by 2, and then obtains this term. This is this 2ASS prime plus 2E prime S. And Bob on this side has a similar value here, that's this V bar, which is, well, you take the V value and then you put it through a randomized double function. So this randomized double function that has a bit of randomness coming in, and that is exactly ensuring it's this trick by Piker to make sure that in the end you have an unbiased key. And then what Bob gets is this V bar, which is, well, this 2ASS prime plus 2ES prime plus 2E double prime. Now these terms here, that's sort of the large term. That's this term that both have the same. And then behind there, there's some error terms. So the idea of this key exchange is that both parties have a value which is, well, similar, but not the same. And then one party sends a bit of extra information over, this V prime here. And this V prime is then being used to agree on an exact value. OK. Now, our contributions was that, first of all, we said we don't really need a failure probability which is that terribly low. We don't need 2 to the minus 131,000. We discussed that with a few people who are actually working on TLS libraries, and we heard that 2 to the minus 60 is just fine. If something happens with probability 2 to the minus 60, there's failures that happen more often, and then, well, you just retry. You just agree on a new, well, you run the whole thing again. Then we came up with a very tight analysis of what the failure probability actually is, which allowed us to choose the other parameters to actually get to this failure probability. We decided to keep the dimension, so 1024 as the dimension n, but choose q much, much smaller. Now, typically in cryptography, when you make parameters smaller, things become less secure. And here, exactly the opposite happens. When you make q smaller, the intuition is that then the noise matters more. So what you care about is how much does the noise matter in relation to the value q. So if you make q smaller, everything becomes more secure. Also, messages become shorter. And, well, if you work with smaller values, there's some speed-ups. We decided to analyze the post-quantum security. So we said we're not so interested in what can an attacker do today, but what does an attacker do, breaking this maybe in a few years with a quantum computer. Then we said we don't want this Gaussian noise, because it's really hard to sample. And quite a bit of the inefficiency of this BCNS proposal that I showed before came from the fact that they were using a discrete Gaussian. And we realized that you need something which looks kind of Gaussian, but it doesn't have to be a real Gaussian. So you just say, OK, take two k-bit integers, a and b, compute the Hamming weight of them, and then just subtract the Hamming weights. That looks kind of Gaussian. And that's just good enough. And there's a proof that this is good enough in the paper. And then we said we choose a fresh A for every protocol run, which is obviously making things slower. I mean, if you need to sample a new A every time, it's definitely slower. I will come back to why we did this later. And then we encode polynomials that we send over the channel in the NTT domain. So basically, you can think of this as we take a polynomial and run an FFT over it. And that allows us to do very efficient multiplications and actually save a few of those FFT transformations, which is the main arithmetic cost. And then we implemented the whole thing. And, well, I'll say a bit about the speed later. So now I can't really talk about any of these contributions in very much detail. The paper has very nice pictures on all of this. I can't show those, that would take too much time. So we'll give a bit of an idea of what each of these contributions means and then see where we end up in the end in terms of performance and security. First, this is what our protocol now looks like. You see that up here, there's no system parameter anymore. What we get instead is that Alice, the server, is taking a seed and then is expanding this seed through Shake128. That's an extendable output function from the FIPS 202 standard. And then, well, is parsing this into a uniformly distributed A and is sending the seed over so that Bob can do the same on that side. What also changed compared to the previous protocol is that, well, we're choosing noise from a different distribution. And down here, this error reconciliation works in a different way. And I will come back to that. So we don't have this randomized doubling anymore. This is now replaced by something that we call helprec. It's somewhat of a generalized version of this. And then in the end, both parties have a value, well, v and v prime. They're very similar as before, except that the factor 2 is missing. And then they have this vector R of reconciliation information that they use to extract K here. And that one, as part of the protocol, we put through a final hash. And we use SHA-3 there. That's essentially the protocol. Now this error reconciliation, well, as I said, we agree on a somewhat similar value on both sides, and we need to have the same, well, we need to extract a common key from that. And what is known is that, well, you need to send some additional information, this R. You can't do it without. It's, by the way, a very fun exercise to think through why you can't. Spend a few hours thinking this through, and at some point convince myself that it's really not possible. And I think everybody working in this field at some point did. So what is known is that you can extract one bit from each of the coefficients that you find in the literature. It's also known how to extract multiple bits from each coefficient, and then essentially that means that you need to choose slightly lower noise, and that means that you lower the security. But we wanted to do something else, because we had 1024 coefficients sitting around, and we want a post-quantum symmetric key, so we want a 256-bit key. And so what we did is we showed how to extract one bit from multiple coefficients and increase the security. And the idea is, well, specifically we do, well, one bit from 4 coefficients of this noisy polynomial. And it's a method that is inspired by error-correcting codes. What you find in the paper is sort of a 2-dimensional intuition for this, and then really what is happening is a 4-dimensional thing. And then we generalized Piker's approach with this randomized doubling to obtain unbiased keys. Okay, so error reconciliation works. Let's take a look at post-quantum security. And post-quantum security is pretty tricky because many of the algorithms that we know to solve this problem, it is not entirely understood how costly they are for real parameters. So there is some asymptotic estimates, but it's not so clear if you throw in real parameters like this will be the runtime. And in particular, not if you do this whole thing post-quantum, because we don't even know exactly what the quantum computer will look like. So we said, okay, the best algorithm is an algorithm called BKZ. You don't need to understand anything about it. What you need to understand is, as a black box, it's calling an oracle multiple times. And that is the shortest vector problem in a smaller dimension. So that's this SVP oracle here. And we just said, well, we don't really care about how often we need to call this oracle. Let's just say, call it once. Everything else we give to the attacker for free. And we just want to know how long does it take the attacker to solve this SVP oracle once. And that's what we call the SVP, core SVP hardness. And then we look at the asymptotically best algorithm for this in the RAM model. So we also say, if the attacker needs a huge bunch of storage for this, we give the storage to the attacker for free. We only care about the runtime here. And then we look at the asymptotic runtime and just assume, well, that's going to be the runtime. And the best known cost for this is, well, 2 to the 0.265 n, 4-dimension n. The best plausible quantum cost we also analyzed. And essentially the idea behind this best plausible quantum cost is that before even running anything, the attacker needs a certain set of input, and that is generated classically on a classical computer. There's no quantum computation involved. And the amount of inputs that the attacker needs is this. So that's what we say, even if you find some cool speedups in the later runtime in the sieving, well, you first need to have the input. Okay, and then we analyzed this. We analyzed this for the proposal by Boss, Costello, Neric, and Stabila, and we analyzed this for the New Hope parameters. And what we see here that the best known classical attack without involving a quantum computer, we get a bit security of 86 for BCNS and almost 300 for New Hope. Now, as I said, this is for shorter messages and, well, we will see quite a bit of faster computation. And even if we go for the best plausible, so not even currently clear how this would work, post-quantum or quantum computation algorithm, we get something like 200 bits of security here. Now, this does not mean that you can actually break BCNS in 2 to the 86. As I said before, we give a whole lot of things for free to the attacker. So it could well be that the analysis that BCNS got with 128 bits of security is just fine if you try to get a somewhat tighter analysis. We just said we want lower bounds on the bit security here and be done with it. Okay. Now I mentioned that we don't pick a fixed system parameter A. And one reason for this is that it's very hard for cryptographers to agree on a fixed random system parameter. If you ask around here, then everybody would somehow probably come up with some system parameter, and then afterwards you have to agree. And everybody who comes up with one parameter needs to convince everyone else that I don't have a backdoor. It's not so easy. There is this so-called nothing up my sleeves approach where, well, you take some digits of pi, for example, you feed them through a hash function, and even then you can write scientific papers about how to attack this approach. So it's really, really hard to get cryptographers to agree on this. Even if you manage to do this, there's another problem. And this other problem is assume that lattice cryptanalysis really improves, and there are possibly really big improvements ahead. It's not like it's really well understood how hard these things are. And let's say maybe there is an algorithm in, say, 20 years, maybe 30 years, that can solve these problems, but not almost for free, but maybe it takes a year to compute. Now, if you choose a fixed A, you do this computation once, which costs a year, maybe on a huge supercomputer in 20, 30 years, and then afterwards you can just break every single key exchange. Because the computation that you need to do, the expensive one, only depends on A. Now, if you choose a different one, different A for each key exchange, then you would need to do a computation of 1 year for each single key exchange, which is an additional safeguard. So this attack that I just sketched is in the spirit of a logjam attack, where you also had like this huge pre-computation done once, and then once this was done and you had this pre-computation result sitting around, you could afterwards attack, well, every single Diffie-Hellman key exchange if they were using the same system parameter, in that case, the prime number. So as I said, solution in New Hope is, well, expand a fresh seed every single time. And then, well, expand it through the SHAKE128 XOF. You can cache this. So if you have a server that is really bottlenecked by computations, then the server can just say, I'm caching this for an hour, and then an attacker in, say, 20, 30 years with this advanced algorithm that we don't even know whether it will exist needs to do 1 year of computation per hour. That's still not so bad. One word of warning, you must not reuse the keys and the noise. So this S and this E and this S prime, E prime, and E double prime. In Diffie-Hellman, or elliptic curve Diffie-Hellman, it's common optimization to reuse ephemeral keys for like an hour or so, which in SSL libraries is happening on a somewhat higher level. Now, if you replace this or if you add in post-quantum, say, New Hope key exchange there, make very sure that you're not reusing these secrets. Then things become insecure. Okay, I said we implemented the whole thing. And the costly operations in there are these multiplications in this polynomial ring. And we chose parameters such that we can do this through something which is, well, a very, very efficient number theoretic transform. So essentially the idea is if you have to take two polynomials, you send them through an FFT, then you multiply coefficient-wise, and you do then an inverse FFT of the result. And FFT in a finite field is, well, becomes an entity, and this one is really, really fast. And because we're sending polynomials in entity domain, we don't on one side first transform back, and then on the next side transform again to entity domain. We just leave it there, which saves us 2 of the required entities. We came up with a C reference implementation, and when writing this, we really kept in mind that this should be portable also to small embedded devices. So we only use 16-bit and 32-bit integers, except in Keccak, so in the final hashing that is inherently 64-bit arithmetic, so we left that from the implementation that the Keccak designers came up with. There's no division operator, there's no modulo operator in the whole thing, so the whole modulo arithmetic is done just through multiplications. We use a trick for efficient reductions inside the entity, modular reductions. We use Montgomery representation. And for this noise sampling, what we use is ChaCha20, which is very portable, very fast, very easily protected against timing attacks. We also optimized this for large Intel processors and used the AVX2 vector instruction set, basically through all computationally expensive tasks. So the entity is vectorized, the centered binomial sampling is vectorized, error reconciliation is vectorized, noise sampling. Here we use AES-256 for noise sampling because on all these processors there is AES-256 in hardware, or AES in hardware. And as you can see, it doesn't matter, these are compatible. This is a local decision how you sample your noise. It's your local secret. So you can just use whatever you have sitting around as an efficient RNG. So here's the performance as opposed to the performance of BCNS. So you can see that our C reference implementation of the key generation and this shared key computation on the client side is about an order of magnitude faster than the BCNS proposal. And then our AVX2 implementation, is still, a factor of 3 roughly faster than our C implementation. For the shared key, we unfortunately did not get exactly to the order of magnitude speed up, but still it's quite a bit faster, about 5 times faster. Now these numbers here include, on both the server side and the client side, this generation of A on both sides, which BCNS don't have, and which, at least on the server side, we could cache. But, we didn't really bother. If cycles don't tell you all that much on Intel processors, to give you an idea, the currently fastest thing that you can use for key exchange in TLS, that would be the X25519 elliptic curve scalar multiplication. And if you use purely ephemeral things with no caching, then each party would need to do 2 scalar multiplications, so 2 times this. So in other words, New Hope is faster than what is currently included. Okay, now at this point of the talk, I should maybe answer the question whether you should be using this. And then I would give you a super biased author opinion here whether you should be using it. And I'm very lucky that I don't have to do this, because it is currently being used. So on July 7, Google announced that they would be running an experiment. It's a 2-year experiment between Chrome Canary and some Google services. And they're running TLS with a new key exchange hybrid, which they call CEC PQ1. And that hybrid is using exactly the X25519 elliptic curve key exchange that I mentioned before, and New Hope. And if you can run Google Canary, which I cannot because I have Linux and it's apparently not supported, then you can see pictures like this where actually you see that the protocol is TLS 1.2 with the key exchange being something that uses New Hope. Now, Google here is actually doing exactly what we would also recommend. Namely, you should be using it if you need post-quantum key exchange, ephemeral key exchange now, which might be because you have users that really care about long-term security, or because you want to experiment early to figure out whether the larger messages, so messages become larger compared to ECC, whether your system can handle that. That's actually what Google wants to also try out with this experiment. Then the second thing is you should always combine it with a key exchange that we're currently using, so X25519, to be sure that you're not lowering security by using something which is still, it feels a bit experimental. And then the third thing is Google said they're doing this for 2 years, and they're hoping that there will be something better in 2 years. And I would say this is entirely realistic. So if you do it, then write it in a modular way so that you can plug in something else. If you're interested in this, if you're interested in learning more about New Hope, or if you're interested in playing with the software, it's both online. Software is in the public domain. It's both for download on cryptojedi.org. And after we put this paper online, several people followed up on this. There's now more software. There's software by Erdem, who's also an author of this paper, and Philip Jakubait, and myself. We optimized this also for embedded ARM processors. Yawning Angel optimized it in Go. Isis Lovecraft wrote a Rust implementation. Riz Weatherley wrote a Java implementation. And only very recently I learned that Alexander Faray wrote an Erlang implementation of New Hope. So I know that most of this code is in public domain. For the ones that I didn't write, please double check on the respective websites. If you have any questions about this, then of course I'm open for questions now. You can also write us an email to newhope@cryptojedi.org. And for now, I thank you for your attention.
Sorry. Dmitry Kovatovich, Luxembourg. What are the units of cost where you measure the security?
So that would be the asymptotic complexity of the sieving algorithm. And then this is hiding all kind of linear factors that you might want to throw in there. So this is so you would need something like 2 to the 199 operations, where these operations are actually pretty large things. But we give those large things to the attacker for free. We just say it's an operation.
Some small atomic operations.
They're, as far as I understand, not all that small, and they also involve pretty big access to pretty big memory, even if you want to do it. But let's say small in some sense of small, yes. But more costly than, for example, in a call to AES.
Interesting, how much memory, just for curiosity?
Yeah.
How much memory?
I don't know. Okay. I'd have to take a look at it.
Mike Petula from West Point. Hi, Peter. Two related questions. Have you talked to any other TLS implementations other than Boring SSL? And then are we going to see this in SALT as well?
We had a bit of an exchange with the people who did the BCNS implementation. And we also discussed whether we should integrate it in OpenSSL. Now, I myself have very little experience with writing code for OpenSSL. There's some code that I wrote in OpenSSL, but other people integrated it. And I looked at the integration in OpenSSL. I found a large cascade of if-defs where I realized that it's very easy to screw this up. And I decided that if we're doing this, I'm interested in helping with this, but I'd really rather have someone who's really familiar with OpenSSL. Will we see this in SALT? I think currently our priorities for SALT are others. I think maybe at some point when SALT goes completely post-quantum, I would hope that there's something better than that, but it's not entirely impossible.
Is the post-quantum some time away, do you think? Or
you mean post-quantum SALT?
Yeah.
I don't see this happening this year.
Okay. I'm not going to hold you to it, but okay. Thanks, Peter.
Kenny Patterson from Royal Holloway. I got a bit confused about some of your security analysis, so could you put slide 10 up for me? Thanks. I think it was slide 10. Yeah, okay, so I guess the first question is, and you didn't explicitly mention this, but I assume it's true. Do you have a security proof that reduces to the hardness of ring LWE for your?
There is a security proof in the original paper by Picard. Yeah.
And does that proof carry over to your slightly different protocol?
There is. So we don't have this average case to worst case reductions with the parameters that we choose. We do show that if we don't use Gaussian noise, that the advantage of an attacker is small. So you can say if there is an algorithm distinguishing with Gaussian noise, then the same algorithm has with a certain probability, then with a certain slightly lower probability, you can also distinguish with this noise.
Because the binomial distribution is close to the Gaussian distribution,
yes.
Right? But that's not the same as a security proof.
You shouldn't be using this in signatures, though.
No.
So in signatures, this is a completely different situation.
Okay.
So this is something which actually, even if you use it for if you did a CCA transformation of this to reuse keys at some point and have long-term keys, it's not entirely clear to me what happens. So this is something only for the purely ephemeral situations. At least I won't make any statements beyond that.
So let's suppose that we assume that proof carries over. Let's be optimistic. You have this quite conservative analysis here where you're saying, well, let's just count the cost of one SVP oracle and call that the security of the scheme. But if you take into account the cost of the reduction in the security proof, then maybe you go in a different direction with your parameters.
Completely.
So can you just say a little bit more about that for this audience and what's missing there?
Okay, so if you look at the tightness of the reductions, the parameters are not chosen to take those into account. What we're looking at is the best algorithms that we know to solve this problem and not another problem that it's being reduced to. But just much smaller or something like that. Also, something that I should mention here, we look at this ring LWE instance as an LWE instance.
Right, that was my next question.
Yeah. Very good.
So you're implicitly assuming that
Yes.
ring LWE is just as hard as LWE.
Yes, and I would really want to see much, much more research on this. So any PhD student who needs a really cool topic on asymmetric cryptanalysis, I think this is really something extremely important to look at, because this is not clear that this actually holds. At the moment, there are no better algorithms. There's no algorithm that would exploit the structure, but I would be extremely excited to see such an algorithm.
Okay.
Because it would really improve our understanding.
So the chair isn't stopping me asking questions.
Yeah,
and
last one.
There's
We'll
no one
get
behind
one
me.
more. Yeah.
So you talked about the number of cycles you needed to run the key exchange protocol. You didn't talk about the bandwidth consumption. I wonder why.
About
The amount of bandwidth that your protocol consumes when you send messages on the network.
So what we're sending is about 2 kilobytes in each direction.
Okay.
That's improving by a bit more than a factor of 2 compared to BCNS, and it's way, way worse than elliptic curve cryptography.
Sure, like 10
That's
times or something, but
almost 100 times.
100 times. Okay.
I mean, you get 32 bytes
Oh,
each
yeah,
way
sorry,
in elliptic curve cryptography.
Okay.
So so I think what we will have to live with, at least from everything I understand right now in a post-quantum world, is things will become larger. Messages will become larger.
Okay. Thank you very much. Thanks.
Hello, José Fernandez up with École Polytechnique de Montréal. There are applications where where key exchange is not going to cut it, where you're going to need certificates or some certificate-based public key implementation. So I'm wondering what is standing in the way of using this as a certificate-based public key infrastructure? Is it just a certificate size, or is there something else that you didn't talk here about?
So you mean using this with long-term keys, basically, that have signatures on them?
Yeah.
The very basic idea is that what an attacker can do, so you choose your long-term key, and I'm communicating to you, and I can choose noise such that with relatively high probability the key exchange fails. And this probability depends on your key. Now I keep just sending you messages and play with the noise and then keep learning about your key. If I do this plain thing. Now if we do this ephemeral, then I can learn something about your key by doing this, but also afterwards you throw it away. The key exchange failed and it doesn't matter at all. Okay. But you can't reuse the keys for roughly that reason. There are transformations for this, but this is something beyond the paper that we currently have.
Okay, so it's because of the noise model and the fact that it's not deterministic as in standard PKI.
It is really because this has only a chosen plaintext security and no chosen ciphertext security.
Okay, thanks.
Yeah.
So let me take one last question. So the failure probability you settled on was 2 to the negative 60, which still strikes me as a extremely low failure probability. Because the consequences of a failure are just try it again, right? There's no security loss, there's no big harm. So if you set it to, say, 2 to the negative 8, some ridiculously high failure rate, would there be benefits of doing that, given the cost of failure is so low?
You can, so if you do this, then the obvious thing that you can do is you can increase the noise. And then you get even more security. Now, this is not necessarily something that we were still aiming for at something like 255 bits. Well, at some point you say it's enough. What you can maybe do is you can make the dimensions smaller. And what the paper has is we have an instantiation with n equals 512. And we're aiming for the same error probability, failure probability, sorry. And we don't get 128 bits of post-quantum security with this conservative estimates. Now, we could have argued that somewhat tighter analysis would still give us good security there. And then we could have maybe said that 2 to the minus 30, for example, would still be okay and increase the noise a bit and puzzle this together. For me, the only reason to use this at the moment is really long-term security. And I'm expecting some advances in cryptanalysis there. So I would really want to go for really conservative parameters, in particular because it feels like there's no reason to not do it. The only messages become roughly half the size. But it somehow feels more comfortable for long-term security to stay away from that.
Thank you. So let's thank our speaker again.